Okay, so good afternoon. My name is Lisa, and I would like to welcome everyone on behalf, of course, of Bioenergy Australia. So first of all, I would like to inform you that, as I said, this webinar will be recorded, and we will share the recording after the webinar. So you can have a look again at the webinar if you missed something. You should all be muted during the presentation to avoid background noise. And as I said at the beginning, your cameras should be off to ensure a sort of good quality of the call. And it's good to see that many more people are still joining, which is great. So questions will be right at the end after the last presentation. And I would ask to those who want to ask a question just to type the name and organization in the chat box that you should see on the right-hand side of your control panel. So I'm aware more or less of how many people are interested in asking questions. Of course, you can do that at any time during the webinar, but as I said, we will get to the answers at the end of the webinar. So in terms of background for this webinar, as you might be aware, Bioenergy Australia participates in 7 tasks of the International Energy Agency Bioenergy Program. And as part of this program, basically we organize every year webinar series with the Australian representatives and of course other speakers that are involved in the sector. This specific webinar is supported by the IEA Bioenergy Task 44, which is focused on flexible bioenergy and system integration. And in particular today, we will be talking about flexible bioenergy system in the agricultural sector. So the Australian representative in this task is Amy Philbrook, who is also the co-organizer for this event. Thanks, Amy. She will provide an overview of the task and basically the work they are doing, and she will also facilitate presentations and introduce our amazing speakers today. So as you can see in the slide, we have a domestic speaker, Richard Gorman from CalFresh, but also 2 international speakers. So we have Rasmus Eisted from Denmark and Ian Rowe from US. So thank you really to all the speakers for taking the time to present today. And I think I can now hand it over to Amy. All yours.
Great. Thanks, Lisa. Tara, do you want to stop presenting?
Sorry, Amy, are you talking to me?
No, Richard. I'm just going to. I was just asking Tara to stop presenting. So, thanks, Lisa, for organizing this event. I think this topic is getting a lot of traction, and that's evidenced by the number of participants we have today. So, as Lisa said, I'm the Australian representative on IEA Bioenergy Task 44. You might also know me from working at ARENA in the business development team. So I'm quickly going to introduce what Bioenergy Australia is doing with the IEA. So Bioenergy Australia coordinates bioenergy past participation from Australia. And Australia currently participates in 7 different tasks. I'm not going to go through those today, but Lisa will be sharing the slides. And it also has on the slide the person that represents that task. And I would just really encourage anyone that was interested in knowing more about the task to go through Lisa or contact the Australian representative because there's a lot of good knowledge that's being generated through this work. So IEA Task 44, it's a relatively new task at the IEA, and it's titled Flexible Bioenergy and System Integration. And it really has been developed on the basis that bioenergy does offer a lot of different potentials in terms of not just providing electricity and heat, but can also provide different storage mechanisms and also can provide complementary system integration. So I've just highlighted the last of the bullets that has to do with this seminar today. And it really is this use of Digestate that has brought this topic of interest to Bioenergy Australia. So first, I'd like to just do a big shout out to Lisa for organizing this, and of course all the other webinars. But as I said, there was a lot of interest in attending this, and as you can see, we have very good attendance. The first presenter today is from Australia, Richard Gorman, and Richard is the CEO and co-owner of CalFresh, and that's a Queensland-based vegetable farming company which grows and sells produce to retail and food customers in Australia and overseas. And I just want to say that, you know, it's the work that Richard and his team that are doing that has really inspired the topic today. So, Richard, I'd just like to invite you to give your presentation and perhaps give an introduction on CalFresh as well.
Thanks. The CalFresh is a vertically integrated vegetable processing. We grow, pack and sell vegetables. Now, part of our future is further processing, which involves more buildings, more supply, and above else, more energy, so energy to process the crops, and so that's provided us with a few challenges. So one of the major challenges was we developed a plan to build what we call the Scenic Rim Agricultural Industrial Precinct. It's an industrial development focused on people who need to grow, pack and sell produce, but also the support services that we require and getting them close to us. So we're, as a business, our main base is 75 kilometres southwest of Brisbane, which is the capital city of Queensland, in North Queensland, in Northern Australia. And so we approached the state government about how we could pull this off. And we've been working with the Coordinator General of our state for the last nearly 18 months, hand in hand, to try and get this project up. Now, the cornerstone idea of that is to value add the ingredients where they're grown. But to do that, we needed, you know, control of our utilities in a regional area. So our plans to create 16 freehold lots between 2,000 square metres and 5 hectares in size. But it's the communal utilities and renewable power that's generated on site that gives us our edge over the standard industrial estate. The key to, we're very much a community-based organisation where we've always been known in our area to think about the rural industry that supports us, and as well as ourselves, and then making sure that we're growing people as well as food. So we've got to make sure that we're looking after the people in our community, particularly the younger people, then trying to stay ahead of the game. And that's led us to giving ourselves some goals of what to do over the next 10 years around creating jobs, but also, you know, building the capturing that value-added dollar and keeping it in our region. Some of those challenges that we face is, you know, as the specifications for what we grow get harder and tougher, we've been quite focused on creating use for our waste, but also we've now realised, once we started looking into anaerobic digestion, you provide a waste solution for other people around you. So we saw the opportunity to create base load renewable energy. that got us to thinking, well, look, we're energy producers, so whether you're eating it or you're putting it through your digester and we're consuming it to cool the crops or heat the crops, to us it's all energy. And then the other energy that we consume a lot of is nutrition in the way we feed our crops. In the last 5 years, we've really increased the amount of organic fertiliser that we use. So currently we're one of the largest users of a bioproduct of ethanol production called Dunder out of a ethanol plant in Serena. And so we've learned to use the high volume, low concentrated liquid forms of organic fertiliser. And I guess we thought, well, let's have a look at co-digesting not just our waste, but some of our energy crop that we can grow in rotation and see what we can produce out the other end of it. And let's put a value on that as a fertiliser. So co-digestion ticked a few boxes for us, and on this slide you can see it. So it delivers the renewable energy to us, but also allows scope for other people to move into the precinct. When we approached Energex, they put forward their concept, and basically you end up with a low-cost grid connection, because in regional areas you don't have large power lines. So you might not be doing lots of megawatts per hour, but you do them 24/7, and that's what's really important. And it's also independent of geography and season, so it doesn't matter if it's day or night, doesn't matter where you are, these things run quite stable. It doesn't matter about the wind, and it doesn't matter about the sun. Becoming a waste diversion option for some of the commercial waste collectors, we focused very heavily on liquid fats out of the liquid waste streams in our area around us. So partnering with Cleanaway early on just to identify how much of that is there. You can collect a gate fee for that. So that also really helped the commercials of our project. So being able to have multiple revenue streams, like e.g. not just our power bill and not just our fertiliser bill, but having a gate fee from diverting urban waste sort of really helps it stack up. And when we come to Digestate, which is, I guess, what the interesting thing we want to talk about today, we started valuing the Digestate based on the nutrient contained within it. And we've come up with a basic strategy around what to do with Digestate. And this diagram, the top part of it's quite easy, and then you get to the wet continuous digestion, and then we start with separation. And what we've done is we've ended up with 3 streams of what we think we can use. So the solid Digestate can come out, and we can apply that, we can screen that out from the slurry, and after it's been pasteurised, we're quite confident in putting that onto our crops. So we don't have the ability to allow contamination onto our land. So some of the land that we use for intensive horticulture is some of the most expensive land in Australia. So even 1% contamination is too much. So cleaning up the pathogens and controlling what substrates go in is quite important, and that's what we've been focusing on. Using the excess heat from the CHP to control dry the product and pelletising that product, that's not new. That's not new technology, but it's something that we're working on. And the exciting bit for us is that gives us a base product that works well with, we call them biological additives. You can call them probiotics. Basically, it's beneficial microbes that we use to help our plants grow. Putting that product and combining it with organic matter and a small amount of nutrient is almost the perfect delivery method to deliver that biological activity to the soil pre-plant. And that's the new technology in agriculture that excites us the most. It's become very, very beneficial to our current cropping program. So we are looking at advancing that technology further. So we're not just delivering some humus or organic matter to the soil, we're not just delivering nutrient, we're also delivering those biological additives. There's a lot of work to be done there, but with initial discussions with the university, where I'm an alumni of, the University of Queensland, they're at the same time starting to work in that space as well. So that biological additive value takes a product that's potentially worth $20 to $30 a tonne in its raw state. You dry it and you condense it down. You know, we're starting to value this product at $250 to $300 a tonne. Now, that makes these plants go from, you know, something that's viable to something that's quite exciting to be part of. Of course, we're also left with the liquid digestate. Now, a lot of our in-crop nutrition is currently chemical, where we inject it into irrigation streams. Creating new systems for that is something that we've already done using the byproduct out of ethanol production. There's a lot of benefits to that too. It's just not widely adopted within current agricultural practice. So there's some of the risks associated with the renewable energy project. But there's so many benefits, I guess, to understanding and creating these solutions. We've decided to go, well, let's start with what we know we can do straight away and do it at a high volume, and then over the course of the first few years of operation, focus on creating those solutions and making sure, like, the big challenge for industry will be keeping contamination out of the environment. Like, we're probably a good case to go forward with, because the environment that we have to protect is the one we've already paid for. You know, we're going to start with our own farms first. I'll be really interested to hear what people from other countries here today say, but that's probably the biggest challenge for us in moving forward. There's a lot of positives around carbon emissions reduction with these types of fertilisers. Travelling through Northern Europe, looking at digesters, you know, I was quite amazed that base fertiliser just wasn't purchased in a lot of the areas I visited, particularly in northern Germany. So that excites us. When you start to measure exactly how much extra carbon you can store in your soil, without going into the benefits that actually gives us within our cropping cycle, you know, they're not small amounts of tonnes. They're large volumes. And just to give you a rough idea, for every 1% higher of organic matter we get in our soil, we can store up to 140,000 litres of extra water per hectare. Now, that may not sound like a big thing, but that means a lot in agriculture. So I guess that's where we're at. We're very thankful for the state government for all their help in getting us through the environmental approvals. We're excited about the carbon abatement, and we're very committed to go from our base of using organic fertiliser that we currently use and to transition a lot of that into Digestate. Thank you, Amy.
Thanks, Richard. And as I said, we're going to leave questions to the end. But to wrap up the Australian perspective, we just wanted to ask John Norwood to talk about some technology solutions.
Hi, it's nice to meet you all. Can you hear me?
Yeah, we can hear you.
Yeah, look, I was just listening to what Richard was saying, and he's got the essence of everything that's required for his project, which is fabulous. I guess I wanted to just talk about why anaerobic digestion and agriculture is the perfect fit compared to anything else. And it probably, it does come from there's a few good reasons, and a big one is the nutrient capacity, that, you know, what is on the farm can almost stay on the farm. But it's also about energy usage. And if we thought about anaerobics, maybe on a city fringe doing sewage and organic waste. You think, well, what can we do with that? Ultimately, we'd make energy with it and pump it into the grid, of course, but that's about all we can do. And all we've done on the side is created a digestate issue that we have to do something with that wastewater. And also, we have not been able to use all that waste heat on a city fringe. Well, it's pretty rare that we could use the waste heat on a city fringe. And the waste heat is possibly 3 times as much as the electrical power or electrical energy. So, you know, if we can use AD on the farm and that digestate, we've got a 4-to-1 improvement in energy utilization of that organic. But the nutrient ability to grow and to do soil remediation and mulching and all of those returns, which ultimately grow again. So the ability to grow again and absorb the sun to create more energy in a crop is absolutely important. So, you know, in my head, AD is an agricultural technology more than anything else, and it should be encouraged. So what Richard's doing is fabulous.
Great.
The other thing is that speaking about growing food and new ways of growing food and the problems that maybe broadacre cropping has come across, if we do have a produce your own energy on the farm system with organics like this, then it allows us to, it gives us energy in regional areas that where the energy is not there. It allows us to do some higher density growing as well. So if we've got energy, we can put crops under lights, which helps the seasonal variation in growing. And we can also seal up our greenhouse, so we've got less issue with the pesticides and fungicides and everything else. So we can energize more of a protected cropping situation as well, whether it's for seedlings or a very high valued crop. That makes it all possible in the bush where it wasn't possible before. So AD in regional areas opens up lots of possibilities, and yeah, we've done some extensive modelling on all of these things at a high resolution, almost to every hour of the year. But there's the obvious things that I've talked about just make it a shoe-in for agriculture.
Thanks, John. And yeah, I would just invite John to take questions at the end as well. So the next speaker is Rasmus. He's an expert on circular economy and waste management in the Danish Environmental Protection Agency. Rasmus has a PhD on life cycle assessment of waste management systems. So thanks for offering to speak today, Rasmus, and very keen to hear the perspective from Denmark.
Thank you, and thank you for the invitation. I hope you hear me clearly. I represent the Danish authorities, and we work with the regulation and monitoring of physical impurities in biomass. And just to give you a short little overview, Denmark is only 0.5% of Australia, and we are approximately 5.8 million inhabitants and 2.5 million households. And that's important when it comes to waste management. The Danish authorities made some years ago a plan for turning from huge use of incineration to become more recyclables and use more recycling of our materials in the waste. That includes specifically organic waste, because organic waste is a huge part of the waste stream. And turning over from incineration to more recycling has given us some different kind of issues we have to deal with. And over the time, we have dealing more and more with circular economy, and we have even made a strategy for the circular economy and also for how to deal with plastic. And that's an important part of the physical impurities. And now we're waiting for the next waste management plan. Sorry. The Danish waste model is based on the waste hierarchy and is also based on the principle of the polluter pays. And we are trying to go upwards the hierarchy. When it comes to organic waste is considered as material recovery, even though when we do the accounting, we account it as recycling. And that is because we want to have that organic waste into the system. It is not material recycling as if it was glass and metal, but it is still recovery of materials, and it will work as fertilizers in farmland, and that's why we try to put it into the system anyway. Not again. One important thing when it comes to the Danish waste model is that household waste is a municipal scheme. It is collected in a municipal scheme, so that has one stream. And businesses, that is a private scheme. So different kind of service sectors, construction and demolishing and agriculture is their own system, and they have private collectors. And they also is a part of the pre-treatment system and become a part of the whole waste treatment system. But the collection is very different from between the household and the businesses, and that's the important part here. I will come back to that. If we look into Denmark, when it comes to organic waste used as material recovery and energy production, a couple of years ago, this was the picture. All the green municipalities are collecting organic waste from the households, and it is put into different kind of systems where it produces biogas in one way or another. During the next couple of years, the whole country has to be covered. That is an EU directive that says that we have to have a collection of organic waste for all households, and it has to be near the door. So everybody has to collect it. Well, if we look at the feedstock, and now it's going to be more interesting for all of you. We have a lot of pigs in Denmark. Actually, we have 6 times the number of pigs in Denmark is 6 times larger than the number in human inhabitants, and that gives us a lot of manure. It has nearly no physical impurities, so it can just be put into biogas plants. And then we have this focus on circular economy, and it gives us the food waste from the service sector. It has some physical impurities, and then we have industrial food waste. We have also some physical impurities that could be different kind of packaging, and then we have the households, and that's the big challenge in the system in Denmark. Some places, some parts of towns, they are not that good at sorting the waste, so we have a lot of plastic, metal, textiles, glass, all kind of things that go into the household, that goes into the bin for organic waste, and we have to deal with that. And that's where we are looking on different kind of technologies, and we have some very, very good companies in Denmark that have some very, very good pre-treatment systems where these technologies can take out a lot of the impurities, even though there still will be some kind of impurities and that's what we are looking at. This is in a schematic way the system in Denmark. We have the households, the yellow dot, and the businesses that put the organic waste into a pre-treatment system, and that pre-treatment system will come out with a reject, which is not organic waste, that is not possible to lead into the anaerobic digestion. And what we're dealing with is that we're trying to have as much as possible from the reject going into recycling, and as a small part as possible to going into incineration, and that's a very challenging part of it right now. I know that some of our companies are really working on that. Then the material goes into anaerobic digestion, and then it becomes biogas and bio-fertilizers. And this is a huge product, and there's a huge amount of biofertilizer coming with these anaerobic digestions. And that's where it's important that we keep it as clean as possible, so we avoid contamination of the environment. We have put up a quality control system. It is based on the statutory order, and it has a guideline saying that the production line has to take daily samples and mix it into a monthly sample. And what we are looking into here is that we have some content limits where plastic, glass, and composite materials larger than 2 millimeters has a limit of 0.5 weight percentage of dry matter, and the plastic larger than 2 millimeters is only allowed to be 0.15 weight percentage of dry matter, and more important, maximum 1 square centimeter per percent dry matter in 1 liter of biopulp. These are the limits for physical impurities, and the plastic here is very important because that is the one that is contaminating the most. And that's why we are happy to have companies that actually are capable of producing a product that that fits these standards. Where do we do the sampling? Yeah, well, in Denmark, we do the sampling before the anaerobic digestion. And the reason for doing that is that we are not allowed to make a new solution where we just put the contamination into a bigger volume and then just add water or something. So we just have less contamination material in one big batch. So we have to do it before. And here the thing is that the anaerobic digestion in Denmark mostly contains manure from pigs that does not contain any kind of plastic and things like that. So if we take the sample after the anaerobic digestion, we'll see that we can hardly find any impurities. So the sampling on the pre-treated material has to be before it is mixed with manure from the farmers. And that's a very important thing here. So we are not diluting the contaminants into the environment. Yeah, I think that was I wanted to say, and I hope that you got at least something out of it.
No, definitely. That was great. Thanks, Rasmus. And just invite people to put their name in the comment box, and then Lisa will call on you for questions. And just to finish off the Denmark side of things, I think that Lars is on the line and was going to ask add some commercial insights from Denmark.
Yes, hello everybody. When we look at the Danish model, as Rasmus told you about, we have right from the beginning looked at the Digestate as a valuable fertilizer, and that's quite natural. In Denmark we use it also because we have a high focus on circular economy. And to use the Digestate as a fertilizer, you ensure the circular economy. And in Denmark, we use the Digestate as a liquid fertilizer without any problems. And we can see that when we go outside Denmark, it can be more difficult to use the Digestate as a fertilizer, because in some countries it's not allowed to do it. And then you suddenly get a problem with getting rid of the Digestate. And then instead of a valuable fertilizer, you have a problem with could cost you money. So it's also very important for when you look at the commercial sites that you can put some value on your fertilizer, so it can be a kind of income instead of an expense. And as Rasmus also told, in Denmark we have the technology that can ensure that we can remove the contamination. And the company I represent, we have a technology where we only use approximately 30% of what is allowed to have of contamination in the waste, according to the rules that Rasmus just explained.
Great, thanks, Lars. And I might just invite you to stay on for questions at the end as well, if that's okay.
Yes.
Thanks. So our last speaker today is Ian. Ian is a technology manager for the conversion program with the Bioenergy Technology Office at the U.S. Department of Energy. He is a recipient of a Science, Technology, Engineering, and Mathematics Presidential Management Fellowship. Prior to the Department of Energy, Ian obtained his PhD in biochemistry from the University of Maryland. So thanks, Ian. I know it's a funny time of the day. Appreciate you.
No problem. Happy to do it. Okay, let's see. You seeing my screen now?
Not yet.
Okay.
Now we can.
All right, fantastic. Hi, everybody. My name is Ian Rowe. As I said, technology manager at the Bioenergy Technologies Office at DOE. Thanks a lot to Amy and Lisa for reaching out to me and giving me a chance to talk to you all about what it is I do over here. And today specifically, I wanted to talk about flexible bioenergy solutions that can help enable an increasingly renewable electricity grid, and also that can help increase the carbon conversion efficiency of anaerobic digestion. Given the fact that our office is an applied R&D office, that function is to fund applied R&D projects in the middle of the technology readiness level phase, I'm a little less versed in the nationwide policies regarding this than our previous speakers, perhaps, but I can speak to that if people have questions. And but this will be mostly more focused on a few select projects we have. So I'll outline just what the office does, outline the opportunity for AD to support a renewable grid, and then go over a few projects we have. So here's the outline of the Department of Energy structure. That tiny box in the middle is what the Department of Energy decides it needs to spend on energy efficiency and renewable energy, unfortunately. That it comes to about 8% of the entire department's budget. I'm in the Bioenergy Technologies Office, which sits within the Office of Energy Efficiency and Renewable Energy, which is broken out into 3 different wings: renewable electricity generation, so wind, water, solar, geothermal, the energy savings wing, which that's advanced manufacturing, homes and buildings, and lastly, the wing for sustainable transportation, and that would be the Hydrogen Fuel Cell Technologies Office, our Vehicle Technologies Office, so they would do a lot of your batteries type vehicles, batteries and vehicle efficiency improvements, and finally the Bioenergy Technologies Office. That's my office, and the one I'll talk a little bit about here. Notably, while we are under the Sustainable Transportation Office, a lot of our office is about just using renewable carbon as best we can, and not just making fuels, but also products, chemicals, energy, whatever, from biomass. Our motto, I guess you could say, is to develop ways to use abundant renewable biomass resources to make biofuels and products that you would normally get from petroleum. And we have a wide variety of feedstocks we look at here, but mainly non-food sources of biomass, such as dedicated energy crops or forest trimmings, or algae or other waste sources, such as biosolids, fats, oils, greases, foods, and animal waste. We also are looking at increasingly at municipal solid waste and waste gases like CO2, biogas, etc. Just for some scale here, our office is about a $240 million office, and the funds are applied R&D work at both the DOE National Lab infrastructure, which is 17 national labs across the country, And also we fund a lot of that work into the private sector and academia. Roughly half of our money goes to the DOE National Labs and the half goes to private industry or academia. And the office is divided into 5 technology programs: feedstock supply and logistics, so gathering up the biomass, getting it to where it's got to go, pre-processing it. Advanced algae systems, so growing algae, procuring algae, improving algae cultivation systems. The conversion team, that's my team, and that's the actual process of taking whatever biomass, renewable carbon source you have and converting it to fuels, chemicals, and products. Our demonstration and market transformation team, that would be the crew that works on scaling up this technology, taking it from bench scale and figuring out how do you make this something that could be deployed at commercial scale. And lastly, the analysis and sustainability team, which focuses on ensuring that our work is aiming to meet certain techno-economic and life cycle assessment goals. So like I said earlier, we take a broad view of what renewable carbon resources we take in. Of course, we look at the carbon cycle, leveraging the land sector and photosynthesis to generate biomass, and then taking that biomass, converting it to fuels, chemicals, and products. Increasingly lately, we've been looking at other sources of carbon as well. So MSW, waste plastics, whatever. And the idea there being, once it's something we've dug up and brought to the surface, it's part of the biosphere and it's time to deal with it. So we consider that all feedstock we're looking at. Carbon dioxide is another feedstock we've looked at more recently. So we have a lot of efforts on that, and I'll talk about a few of those here. And lastly, most specifically, wet waste, ag waste, et cetera. And that's what the wastewater treatment facility on the right is supposed to show. So we look at a lot of different carbon sources here. And specifically today, I wanted to talk about the opportunities for bioenergy to play into a low carbon grid of the future. So what you see here is a graph. X-axis is time, y-axis is megawatts of electricity generated, and each of the different colors represents a different source of electricity. And there are 3 main options for biomass providing flexibility to such a system. How could a bioenergy support a system like this? In generally, the way we look at it in both DOE and in Task 44, I'd argue, are bioenergy can play a role in dispatchability. So what happens when the sun starts to go down here and you need to ramp up fast? Biomass can play a role there where other renewables maybe have more difficulty. Biomass can provide demand side flexibility such that when you have an opportunity where there are excess renewables here, biomass and biomass related processes have the ability to take those reducing equivalents provided by electricity and convert them to energy. And the third is energy storage. You can leverage bioenergy systems to store energy to use at a time when maybe you don't have sun or wind resources available. So now I'm going to dive into, an example of how AD can provide dispatchability, demand side flexibility, and storage. As I was saying, conventionally, biomass go into anaerobic digestion and generate some a mixture of methane and CO2. You can provide some demand side flexibility in that by when you have a curtailed situation or a situation where electricity is abundant. You can split water, generate hydrogen, and feed that hydrogen to your anaerobic digestion system, essentially adding extra reducing equivalents to the system. And you can increase the carbon conversion efficiency of the process. And instead of it being 2/3 methane, 1/3 CO2 coming out the other end, you can drive closer and closer to getting more and more of your carbon getting into methane versus into CO2. So now a few specific projects that we have on this. The next 2 I'm going to talk about come from a funding opportunity announcement we put out in 2019, where we were specifically asking people to rethink anaerobic digestion. So take an anaerobic digestion process and using electricity to add reducing equivalents to the situation, increase the carbon conversion efficiency of the process. And I'll show you 2 of the more innovative awards we have from that. And these are projects that I currently manage that, well, in a different world, I would go visit regularly, but I haven't gotten to see them yet, but hopefully soon. So this first one is a project at Washington State University, and it's an advanced pretreatment and anaerobic digestion technology for increased conversion of sewage sludge to bio-natural gas at wastewater plants. So the idea here is nominally, they would look at feedstocks such as sewage sludge, wastewater, or food scraps, but also several of these projects that are like this and similar will use ag residues, other agricultural processes such as manure, and feed those into the anaerobic digester. But the two main innovations for this specific project are an advanced wet oxidation and steam explosion pre-treatment of the undigested solids from your first stage AD. So you go through AD once, you get your methane from it, but you also have your residual solids. And the idea here is that those more recalcitrant solids, you would then send them through another process to make the carbon more labile, such that it could go through a secondary process of anaerobic digestion. And then you could collect more methane from that. The second innovation here would be up here in this corner. You see the idea that all the methane gets fed up here, and up here you have a biomethanation reactor, such that you have an immobilized surface where you grow specific organisms that are tethered to that surface. You can feed the system hydrogen, and then the organisms will use that hydrogen and convert the CO2 that is in the biogas to methane. And then you have pipeline grade natural gas. So instead of being 2/3 natural gas, you now have closer to 100%. With the end goal of this project to increase the carbon conversion efficiency to over 70% of the process. The second project that came out of this call for proposals was a novel and viable technology for converting wet organic waste streams to high value products. This was out of the State University of New York, Albany. And there are three main innovations here. Similar, this was taking sludge and food waste up front, but again, this is probably applicable to many other waste that you would commonly put through anaerobic digestion. And to increase the lability of that carbon, they would put it through thermal hydrolysis, which isn't that innovative. There are plenty of processes that do that, like the Canby process, et cetera. But this one added the innovation of the applicants are trying to use sonication as a way to increase the carbon conversion efficiency. So you sonicate the incoming carbon stream, you make it more labile for the organisms to convert it to intermediate volatile fatty acids. And then liquid extracted is used on this AD system to remove those volatile fatty acids prior to methanogenesis, such that instead of these volatile fatty acids then getting converted to methane, which is arguably of lower value than VFAs, you can recover your VFAs and also some higher chain alcohols. And then you can send all of those to an upgrading scheme later. That's outside the scope of this project. The other interesting avenue that this project is exploring is sending a stream of the waste coming in to a microbial fuel cell and mixed with a microbial electrosynthesis cell, such that you're generating electricity from the waste stream coming in, and that electricity can be used to electrocatalytically reduce the CO2 in the system to generate even more volatile fatty acids. And then, so overall, you've increased the carbon conversion efficiency of the process. And so most of these are at labs, smaller scale. These efforts are just starting, but they do have requirements to get up to the 50-ish liter scale at the end. So we look forward to these and seeing how they move forward. Lastly, this project is at a larger scale, and I just thought it would be relevant to the conversation here. This is with a company maybe many of you are aware of, Electrokea. They're based out of Europe, and they're collaborating with the National Renewable Energy Lab in Golden, Colorado, and Southern California Gas, which is the largest natural gas utility in the U.S., to work on biomethanation. So what you're seeing here is a 700-liter bioreactor set up just outside the National Renewable Energy Lab, and it's coupled with a 250 kilowatt hydrogen electrolyzer. So biogas goes in simultaneously with the hydrogen from the electrolyzer, that in theory you could generate that hydrogen when you have a curtailed situation or a situation where electricity hits a certain low price. You feed both those into the bioreactor, and they can pretty readily produce a stream of pure methane on the other side. So this kind of technology is an example of a lot of the more innovative stuff that we're trying to see how much industrial interest there is out there into scaling up some different biomethanation processes. There's also a few other ones we have at Lawrence Livermore National Lab that are working on an immobilized bed reactor, where you have biology tethered to the reactor instead of a free-floating stir tank type reactor. Anyway, that is all I had. Here's my contact information. Feel free to reach out to me if you have any questions, complaints, or otherwise. And besides that, I'm happy to take questions.
Great. Thanks, Ian. And can I just remind people to ask a question, if you can just go to the chat function, and then Lisa will manage that by calling on you to unmute yourself and ask your question. So Lisa, I'll just hand over you for questions. A big thank you, especially to the international guys that are doing this at the wrong time of the day, for really
Thank you, Amy, and thank you very much to all the speakers. As Amy mentioned, sometimes we're not really convenient in US and Denmark. As Amy mentioned, we now have question time. Feel free to type name and organization in the chat box. We have already one question from Kelly Wickham from Sustainability Victoria. So Kelly, if you want to unmute yourself, you can directly ask your question. I think this is for Erasmus, or yeah, probably for Erasmus, because that's about regulatory burden on Digestate. Kelly,
yeah, that's right. It was probably for Erasmus or Ian as well.
Yeah.
We're going through this reform phase in Victoria. The EPA's reform agenda was supposed to come down on the 1st of July this year. Obviously, that's not going to happen until next year. The question remains, where does the regulatory burden fall on Digestate in terms of, is it rather on the user to, fulfill the management practice requirements, or is it the producer of the Digestate that has to comply with any sort of regulatory burden?
Yeah, well, as it is right now in Denmark, it is those who are treating the organic waste that has the burden.
Right.
They have to prove that their material is living up to the standard.
Okay, cool. And are there beyond heat treatment, are there other sort of innovative approaches to ensuring that Digestate, as a matter of fact, is coming out, being produced at that level that's considered safe?
Sorry, what was the question?
So yeah, I was just last one was around, what are people doing in terms of treatment besides, are there other methods of treating Digestate as it's produced beyond pasteurization to ensure it's safe to apply?
No. All the organic material coming from households, food waste and things like that, containing plastic and other kind of things, is going through the pre-treatment, where the idea is actually to sort out what is not organic material. Mm-hmm. And then it goes into these biogas digestion, and then we consider it as I wouldn't call it clean, but I would say it is safe to use as fertilizers.
Okay, thanks.
Thank you, Kelly. And maybe Ian, do you have any insights by any chance regarding regulatory burden on digestion in US?
Not much, but I'll give you this, and maybe this will open it up to another question or two. There's a big concern about certain PFAS regulations upcoming in the US for Digestate and what's allowed to go on fields, such that people are no longer accepting it. And that has only come to my attention because now we're getting a lot of applications for people that want to put technology forward to solve this problem. So I'm just curious if any of the other panelists are familiar with current methods to, solve that problem of Digestate.
And I might just open that up to, I know that we have some government representatives from the EPA, if there was anyone that wanted to comment on Ian's observation.
Amy, I'd agree with the Danish philosophy for our project. This is Richard from Calfresh. Analysing your substrates before they come in is the first major step. Then, as a producer of Digestate, we then have to produce the product to a specification. And then, because we're using it on our own farms, we then have also had to develop a management plan that falls under one of our own current quality assurance systems. But when it comes to something like PFAS, with only pasteurisation, you can't treat it. To effectively treat PFAS, you have to go through a level of pyrolysation or gasification, and some of that technology is out there, but it's being developed, but there's not a lot commercially available there.
Okay, that's about the what I had seen. So that's very helpful. Thank you.
Thank you, Richard, and thank you, Ian, for the question as well. So we have a question from Amy.
Yeah, so I think that one of the reasons why we're so interested in Digestate is the potential carbon reduction benefits. And so just wanted to ask the speakers if the use of Digestate, I guess in Denmark in particular, has been driven by eliminating the need for fertilizers made from natural gas.
Can I have the question again?
Yeah, Rasmus. So I was just wondering, in Denmark, is the fact that replacing fertilizers with natural gas, is the carbon benefit taken into account? Is this one of the driving factors?
Well, it might not be the main factor, but of course it's taken into consideration. And right now, where we are trying to make climate act, where we try to find all kind of carbon that is emitted to the climate from Denmark, we are very nitty-gritty and trying to find everything. So right now it has a focus, but that was not the very beginning.
So I can speak for a bit of the U.S. that has this, where there is Digestate application to the land, and that's not. It's more of there are a lot of state and local requirements for landfill diversion of organics, so people aren't allowed to landfill them anymore. So they try to find ways to apply them to the land, which is sad that it takes something to that effect to use this great stream of carbon, but that's where we're at.
Thank you, Ian and Rasmus, and thank you, Amy, for the question. Richard, did you want to add anything?
Yeah, look, what Ian has just pointed out is entirely correct. It's a very, very useful source of carbon, but managing the contamination and treating it to a level that gives people confidence to use that carbon source and the nutrient that comes with it is the big hurdle. That's the thing that you have to really, really be careful of. Like from an agricultural point of view, and I'll put my farming hat on, our business started as farming. We'll never contaminate our soil because our farms are our factories. And the piles that are diverted from landfill, I think you'll see them keep building until there's really good solutions on how to guarantee that we're adding value to our soils. We have the ability to mine carbon from our soil like you can mine it from the ground if we don't practice good agricultural crop rotation. So we need the carbon and we need the nutrient that comes with it. We just have to make sure it's delivered in a way that it's useful. The solution's there. Lots of people in lots of parts of the world can do it and do it. But it's still a challenge. But for us, it's also exciting because we will be able to do it.
Thank you, Richard. So it's probably 3 p.m. already, but I think we have one last question from Ben Carr from Victorian EPA. Ben, would you like to quickly ask your question and then we close?
Yes. We've not been big on digestate application to land. I certainly think we can learn from jurisdictions where they've been doing it for many years successfully. I think we can learn from our aerobic, composting experience, and some of the lessons from that are transferable over to the anaerobic digestion sort of experience and situation as well. Particularly, generally the cleaner the input or feedstock material, the cleaner the output sort of material will be, depending on which particular stream of output it is. And just to sort of comment in, we have a plastic contamination threshold which is considerably smaller than the Danish one. It's 0.05% weight per weight for thin or film plastics in the composting arena, which would probably be transferable over to the anaerobic digestate arena as well. So, and lastly, I think it's good to be cautious in some regards. Like soils and agriculture in Australia is different, very different from in other places in the world. Some of our soils definitely don't have a lot of capacity to deal with a lot of nutrients. They're very leached, and they have, obviously in some instances little capacity to hang on to nutrients. So I think it's good to be cautious, but also learn. Thank you.
Right, thank you very much, Ben. And just checking whether there are any very final comments from the speakers. No. Okay, well then I really want again to thank all the speakers and Amy for facilitating today's webinar. I think we definitely learned that there are great opportunities in terms of digestate for flexible bioenergy. International countries are already doing quite a good job on that, and I think Australia can learn good lessons. As I mentioned at the beginning, all the presentations will be circulated to the attendees after the webinar together with the recording. But feel free to get in touch if you have any additional questions, and if you would like me to put you in touch with the speakers, I'm pretty sure they are happy to potentially follow up offline. So thank you, everyone, and I hope to see you at our next webinar. Thanks. Bye.
Thank you.
Thank you.